Right, good morning, Lower Sixth. Haven't realised I haven't done a video for you for quite a while, but I thought I needed to. I also realised that you probably noticed my hair's gotten quite a lot longer since the last video because I continue to not go to the hairdressers. I've asked Mrs. Cook if she will cut my hair for me, but she hasn't really got around to that yet, and I think it would look even worse. So I'm just going to make do with my hair just being really, really long. You've all got to get on with it. I'm sure you're all the same. Now, anyway, what am I going to talk about today? So I haven't done a video for a little while because I thought I've actually set stuff that I think is relatively understandable. Okay, things like the electromagnetic spectrum, that sort of thing. Once you've done it and they've given you the answers, I'm pretty sure you can basically get the idea. There are some concepts in chemistry which are really, really difficult and they need a video. Some of them I think you can teach yourself. I think what we've been doing is largely that. I would say though that there are one or two concepts from this last week that I think I do just want to go over. So one of them is nucleophilic substitution reactions. That'll be another video. And in today's video I want to go over just very quickly chain reactions. Okay, as in radical chain reactions, that kind of thing. I know we've kind of gone over that already in lessons, I'm pretty sure. Oh, I can hear my son crying. I'm going to shut the door. I know we've kind of gone over that in lessons before, but I just want to make sure we've definitely got that sorted. Okay? So, first of all, just a reminder, what's a radical? Well, here, whoa, trying to get this camera to sort of work. Oops, sounds bad. Here is a molecule of, I think, chlorine, perhaps fluorine. Not sure. Not particularly reactive. If you think about it, it's got a full outer shell of electrons, or both of these have got a full outer, both these atoms have a full outer shell of electrons because they've shared their electrons in the middle there. We're trying to potty train him. I think he may have just had an accident. Oh well, never mind. I should maybe help. I'll pause this and come back in a minute. Right, sorry about that. Yes, he by himself had to sort that. Anyway, so we have this molecule. It is covalently bonded. Everything's got a full outer shell. Everything's stable. Stable electron arrangement. The electrons in here are paired. Everything's relatively stable. It is possible to break this molecule apart, and therefore it is not. Therefore it can react and not stable. But to do that, you have to give it some energy. To be precise, I haven't just blatantly googled this. 159 kilojoules per mole is what you have to give it. Okay, so you give it 159 kilojoules per mole, it can break up. By the way, for a little extension task, it might be interesting to look up, well, what's the frequency of a photon that needs that has 159 kilojoules per mole of energy in it? So what kind of electromagnetic radiation is going to be irradiating this to split it up? You know, is it light? Is it UV? I don't know. I think it's UV is the answer. But anyway, pause it and have a go at that. Did you do it? Okay, good for you. Now, anyway, so let's assume that we have irradiated it with that energy, and we now have. I'm going to reposition the camera. It's not really. Oh, there we go. Is that better? You can see my hands on it a bit more. Yeah. So once we've done that, we then have two atoms which are on their own. And those atoms have an unpaired electron, which is particularly reactive. Okay, because they want that electron to form a pair. So it will just grab onto pretty much anything it can find, including back onto itself. React, form fluorine, that's stable, that's absolutely fine. But it will grab onto other things as well, and cause things which wouldn't normally react, like an alkane, for instance, to suddenly react. So, what we call that then, if we are going to have a chain reaction, I'm in the middle of a chain reaction. Anyway, that's going through my head right now, seriously. If we have our fluorine molecule, oh wow, that really is quite difficult to see on there. There we go, if we have our fluorine molecule, we can irradiate that with some UV, or whatever frequency light you've worked out it needs, and you make two fluorine radicals. The radicals have the dot at the top there. Okay. Now that can then react with something else, like an alkane. So we call that initiation. What you've done there is initiated it. So if I just label that as initiation. Okay, you've started the reaction off. Now, what you'll then need is something to react with. So let's pretend, for the sake of argument, we have some methane. Why not? Because methane's fun. Let's say there's some methane in the upper atmosphere. Doesn't particularly matter what it is. Okay. Now methane comes into contact with our radical, let's say here, right? And they form a chemical bond. So between the hydrogen and the fluorine there is a chemical bond that forms. Now to do that we need to draw half arrows, because a half arrow represents one electron, like so. So you've got a chemical bond forming there. You'll also notice there is an electron, oh I can't do it, it's like mirror image, here, which we have not accounted for. That goes back to our CH3. As a result, we have formed two products. We have, trying to fit it on this one whiteboard. It's the easiest way to draw it. We have one methyl radical and one hydrogen fluoride molecule. Please take note though that we had one radical at the start, we now have one radical at the end. So we've still got a radical. Okay? Now let's say our radical comes across another radical somewhere, another molecule. It doesn't really particularly matter what it is. It could be another methane group, if you like. It doesn't really make a difference. Or whatever it is, it really doesn't matter. But the fact is that it'll then react. I'm going to get used to this new camera eventually. It'll then react again with another methane or whatever it's going to react with. It doesn't really make a difference what it's reacting with. But the point is, because you've produced one radical from one radical, you've still got a radical, right? Make that more clear. Alright, so again, so it reacts the second time, and again you've produced another radical just there. It's like trying to work with a mirror image. So this is called propagation. So every time it reacts, it forms a new radical and then breaks apart more things. Okay, that's called propagation. You'll see that in your textbook as well. So you've initiated it with some UV light, you've propagated it with, but just it reacts in the upper atmosphere. There's a lot of UV in the upper atmosphere that allows a lot of this sort of thing to happen. What's the final stage? So that can happen again and again and again. That cycle just happens again and again. So one chlorine radical, for instance, can just go through lots and lots of ozone. Chlorine will react as ozone, pretty sure that's in your textbook, and it can just go through lots and lots of it. I can't remember the exact numbers. I remember there was 150,000 molecules being somewhere along there. I don't know. Anyway, it does eventually stop, but the way to stop it is called termination, and it's if two radicals react together. Okay, in that case it'll stop, and that's called termination. Okay, that stops the reaction. Now you think, oh, surely that's going to happen pretty quick, but what you've got to remember is in the upper atmosphere, the stratosphere, the concentration of all atoms is very, very low. So you're hardly likely to run into anything. When you do run into something, it's probably not going to be a radical. It's going to be ozone or methane or something like that. But yeah, eventually it'll run into another fluorine, and it'll react, and it'll form a fluorine molecule, and then that's more stable until some more UV shines on it, and it makes another radical again. Two more radicals. It's going to just go mental again. So this is the problem with using chlorofluorocarbons, or CFCs. They are chemicals which go into the upper atmosphere. They are chemicals which are used to be used in refrigerators, and would then float up into the upper atmosphere. And once they got up there, the problem was they were very, very stable chemicals, so it meant that they would get up there, and then once they got up there, they form these radicals, and they just stick around for years and years, decades. They stay around. And just destroy the ozone layer. Hence there's a massive hole in the ozone layer over the Antarctic and a little one over the Arctic. You'll be pleased to note that we've stopped using those sort of things. We use now something called HCFCs, hydrochlorofluorocarbons, which are slightly less stable, and as a result they can't float up to the upper atmosphere, and as a result they're actually far less damaging to the ozone layer, and the ozone hole is actually shrinking. You know, we made some progress on that, so, you know, not too bad. But anyway, those are chain reactions. That's the thing you need to know on that. Next video is going to be on nucleophilic substitution. Right, peace.